So we will leave off and go comet chasing now. Here you can see the flight dynamic team located in the Science Operation and Navigation Center in Toulouse. So in this presentation, I will explain how we have used Scilab for the preparation and the operation of the Philae landing to the comet Churyumov-Gerasimenko, because we have used Scilab a lot during the preparation of this mission. So this presentation is divided in 4 parts. I will present the 2 first parts, and Romain Garmier will present the 2 last parts. So we will start with the generalities on the mission and on the comet, and I will detail the selection of the landing site, and Romain will explain what are the tools we have used for these operations and why we have used Scilab, and we will finish with a quick conclusion. So let's go and present the Rosetta and Philae mission. So why do we go to comets? Why are we interested in comets? It's because they are very primitive objects. They are the most primitive object of the solar system. So they are a kind of fossil of the solar system. So they record information of the physical and chemical processes that occur during the formation of the solar system formation. So, comets have been, usually they come from very far away in space. They will form at very far from the sun. So you have comet in the Oort cloud. It's the limit of the solar system. But you can also find comet in the Kuiper belt. And sometimes they are ejected from the Kuiper belt because of gravity perturbation, and they leave the circular orbit and go to the elliptical orbit, where the perihelion comes closer to the sun, and when the perihelion comes closer to the sun, they start to warp and to sublimate. And so what is the composition of the comet? It's still something to not so well known. So we know that it's mostly water with CO and CO2, with some rocks, dust, and organic material based on the C and carbon and nitrogen. So here you can see the flyby of the comet, the Philae comet by Giotto. Giotto was a European probe launched in 1984, and that reached the Philae comet 2 years after, in 1986. It was only a flyby. It means that Giotto did not orbit around the Philae comet, but passed just through the Philae comet. And at the time, it was possible to make pictures and to put into evidence how it got into the comet. So this was the first European mission to a comet. But there have been there have been several of other missions that are listed here, but none of them orbited a comet nor landed on a comet. So the main science objective of the Rosetta mission, it's now you understand that it's better understanding the formation of the solar system, and also to search for complex organic molecules that could have been brought to Earth when the comet passed next to the Earth, or when the comet hit the Earth in the past. When we ask this question, we want to answer another question. It's did the main ingredient for life did they come from outer space? This is one of the most interesting questions that we try to answer in this mission. So from the science mission, we can derive some mission objective. So the mission objective is to put a probe next to a comet and to be able to study this comet during a length of time which is long enough to do a lot of measurements. And we want also to do these measurements when the comet comes close to the Sun and when the comet starts to sublimate, and in order to collect the volatiles that are ejected by the comet. There was also another mission objective. It's to put a lander on the Sol on the comet itself. And this was achieved last year in November. So, some general quick information about the Rosetta spacecraft. So here on the picture you can see the Rosetta spacecraft, which is basically a cube of 2 meter by 2 meter. And here you can see the Philae lander. So what is specific about the Rosetta spacecraft? It's the length of the solar arrays, very long, because the Rosetta spacecraft has been very far from the Sun. And such arrays, such solar arrays, were needed in order to supply the electrical power that was necessary to maintain the spacecraft in good order. Also, with the Rosetta spacecraft, we can notice that half of the mass is dedicated to propellant, to fuel, because this was needed in order to come next to the comet. There are about 11 instruments on the Rosetta spacecraft. If we look at the characteristic of Philae, it's much smaller. It's about 100 kilometers. There are about also 10 scientific instruments. And we have 2 batteries, one primary battery and one secondary battery. The primary battery has only an autonomy of 50 hours. And also we have some, I mentioned the specific equipment because these are the equipments that didn't work on this mission. It's the active descent system, which is a small thruster, and the harpoons that were needed in order to hold the comet on the soil to hold the Philae on the soil of the comet. So in this mission, there were two world firsts realized by Europe. It was the first time that satellite orbited the comet and still orbits the comet, and it was the first time that a probe landed softly on a comet. You can see on this picture that really this is the feet of Philae. Really, it is on the comet itself. So here quickly some quick description of the Rosetta Odyssey. This journey lasted 10 years. Why did it last so long? It's because the launcher capacity is not sufficient to put you directly on an orbit that intercepts the trajectory of the comet. So in order to gain energy, a well-known strategy has been applied. This strategy consists in doing flyby or gravity assist maneuvers. When you do a gravity assist maneuver, you modify your velocity vector by going close to a planet, and you modify your velocity vector in a sense that you can lose or gain some energy and you use this gain of energy in order to increase the size of your orbit. So, four gravity assist maneuvers were needed in order to approach a comet. So they are listed here. We have first Earth gravity assist, then a Mars gravity assist, and two other Earth gravity assist. And during this this journey, it was also possible to fly by two asteroids, Lutetia asteroid and Cnes asteroid. So it was the opportunity to make some pictures of these asteroids. So the mission started the launch was in 2004 by Ariane 5, and the arrival was last summer in 2014. So here we can see the target. The target is called Churyumov-Gerasimenko, the name of the two persons that discovered the comet. There's also another name which is 67P. We have the comet over our head. Fortunately, we are just a bit away, so there is no risk for us. But you can see the size of the comet. It's big and not so big. It's about 4 kilometers in the wide, in the biggest dimension. The comet is orbiting the Sun in about 6.4 years, and the aphelion, the distance which is further from the Sun, is about 6 astronomical units, and the perihelion that we will reach in May is about 1.2 astronomical units. The comet is very light. The density is between 400 and 500 kilogram per cubic meter, and it has a rotation period about 12 hours. And fortunately for us, the rotation axis was quite stable. Here you have a nice view of the comet with a very irregular shape in two lobes. You can see many geological features, including pits, holes from where the gas are coming out. Because of the size and the density, the weak density, the gravity field is very weak and very irregular, so which complexify a bit the design of trajectory around the comet and to design on the comet. And also there is outgazing. Outgazing, it's a sublimation. It's the ice which is on the main ingredient of the comet, which sublimate and push away the Rosetta and Philae on the approach of comet. Fortunately, at the time of the landing, the outgazing was not so high and was not so much of a problem. So now let's talk about the selection of the landing site. So who was involved in this selection, in these operations? So we had first the Rosetta mission operation center in Darmstadt, in Germany. It's ESA center. We also had to work with the Rosetta Science ground segment in Spain. So the first center is in charge of the Rosetta flight dynamics and is the control center of the Rosetta satellite. And the Rosetta Science ground segment is in charge of the science programmation. If we now look at the control center for the lander, we have the lander control center in Cologne, in Germany, and we have the science, operation, and navigation center in Toulouse. So the SONC. had to provide the data for the selection of the landing site. It's what we did last summer. And we were also in charge of the planification of the scientific instruments on board the lander. We can also see on this map the antenna that were located in Malargüe in Argentina, one antenna in Spain, and the other big antenna in New Norcia in Australia. So let's talk about the landing site selection process. Before Rosetta arrived in the vicinity of the comet, the comet was very poorly known. We knew almost nothing about except its orbit. So, in order to plan a landing on the comet, you had to better characterize the comet, to know its gravity field, to know its outgassing, to know its rotation. So, in order to better characterize the comet, you have to get closer to the comet. But getting closer to the comet, it's taking risk. Taking risk because you are flying in an environment which is not well known. So, the landing site selection, it's a balance between approaching the comet and learning more about the comet. So it's what has been done during the selection, the landing site selection process. This process took about 4 months. So 4 months, it's a very small duration when you consider all the work that had to be done. To characterize the comet, to do the computation needed in order to planify the safe landing. And also, it was quite complex because there are many. It's a very big organization with a lot of many actors. I just said that we have 4 control centers across Europe that have to work together and to planify this operation. So it was really necessary to synchronize all these operations, and for this we had to put in place a kind of operational process, in order to have a chance to achieve this result in such a small time. The main milestone of the landing site selection process were. We had the first milestone in August last year. So at the time, Rosetta was only at 50 kilometers away from the comet. It was August. It was about 80 days before landing. And during this first milestone, we had to select 5 landing sites. So you can see on this picture the 5 candidate sites. Then Rosetta approaches a bit more the comet. It went up to 30 kilometers. We had more data. We had data specific on the 5 landing sites, so we could do a more refined analysis. And based on this more accurate and more refined data, we could select 2 landing sites. And the final meeting, in order to confirm the choice, was at launch minus 30 days, and at the time, Rosetta had to fly up to 10 kilometers away from the comet. You can see on this picture the landing site as seen by the Osiris camera mounted on Rosetta. It was one of the most flatter areas. So the operation for the landing, so it was divided in several phases. We had the separation, descent and landing. So during this phase, that lasted about 10 hours, we were released from the Philae were released from the Rosetta satellite. all the landing gear was deployed about 20 minutes after separation, and there were several instruments that were activated, like some camera that took a picture. Here it's a Rollis camera that took a picture at an altitude of 3 kilometers, and here you have another picture from Rollis at an altitude of 40 meters. Then after landing on the main battery that had only a lifetime of 50 hours, we had the first science sequence. During this phase, all instruments on board the Philae lander were supposed to work, and they all worked. And after, when the primary battery is dead, we have also long-term science where we use the energy from the solar panels in order to recharge the secondary battery. The reality was not as planned, because Philae rebound 3 times. So we had several rebounds. Here you see that this was the targeted point. It was reached very accurately, thanks to AMOC. So we landed at a distance of 70 meters from the targeted point. But the anchoring system didn't work, and because of the low gravity of the comet, Philae rebounded, and at first a collision with the rim of the crater, and second collision here, and went to stop its rebound trajectory in this location about 2 hours after nominal touchdown. Unfortunately, it was stuck in a kind of hole, and it landed in an area that was not very optimal, very well suited from an illumination point of view. We had selected this area that was very well from the illumination point of view, but we arrived in the winter side of the comet. And because of this, its temperature was too low. There was not enough sun on the solar palette, so it was decided to went into a kind of hibernation. And so now I'll give the floor to Romain, that will talk more about our tools and how we have used Scilab in our tools.
Thanks. Okay, so we'll continue with the tools. Yes. So first, on these pictures, you see the control room for the day of the landing. So the flight dynamic team is a small team. We are six persons. So we have 2 computers and 2 additional laptops that we are using for the landing site selection process. Actually, we did a lot of Scilab use during the meeting, because we have a lot of requests for people to characterize candidate landing site. So the flight dynamic team was 3 groups of 2 persons. During the landing site selection process, we were working 24 hours, 20 hours and 24 during 5 to 10 days, depending on the loop. And for the landing operation and first science sequence, it was 24 hours and 24 hours. So we talk now of the flight dynamic system. It's just the name of the set of tools that we are using to realize the operation. So the operating system is Linux. First prototype 20 years old, 95. So it's a long time to realize everything. We have 2 kinds of tools. It's quite artificial, but the critical tools doing computation, so producing numbers, and the visualization tools to analyze what you obtain. So I will speak on this slide of what we are doing with the critical tools. So not about Scilab, I will talk about Scilab later. So these critical tools are highly validated. They are in 1490 with graphical unit interface. They are industrialized and maintained by a contractor. If we have a problem during operation, I don't know, a bug or anomaly, we have to contact the contractor and wait at least 24 hours to have a patch. So as we have 5 days to produce a result, if we have a problem, it's not good at all. So for the landing, we're doing several kinds of computation. First, we have a lot of input preparation. We exchange a lot of data with other teams, scientific data, operational data with European Space Agency and so on. So we have a lot of work to change the format, to adapt it to our internal format and tools. We have some model preparation. We receive, for example, the outgassing from the comet, but we cannot use it directly in our tool. You have to do some processing. You have to be sure that the model is correct, so to validate what we receive. After we do we are computing, for example, the illumination of the comet. As we have solar rays on the lander, we want to have at least 6 hours of light per day. So we have to find the part of the comet where we can have this. Of course, we compute trajectories and landing trajectories and landing conditions. So I think that in typical loop, we are probably computing maybe 1 billion of trajectory. It's very huge computation. We compute the communication slot between Rosetta and Philae. We don't care for Rosetta Earth because it's job of European agency. And we also have to do some prediction of events for a scientific instrument on board Philae. For example, they wanted to know when the comet during the descent will enter the field of view of the camera or leave the field of view of the camera to know when they can do some picture. We also have some work for the first science sequence. One very important task was to determine the lander position and attitude. It was quite a lot of stress because we are supposed to produce this result 6 hours after the landing. So it was a collaborative work with scientists from instrument and so on. Actually, we failed to do it because of the rebound. We didn't receive pictures of the landing site. So it was very difficult to determine how and where we were. So we failed on this part. We were supposed to predict the illumination of the lander. So if you don't know where you are and how you are, you can forget, but we try. And after, we were supposed to establish the communication slot between Rosetta and Philae. This we were able to do it because you can do a few things with not too much accuracy, but you can say at 1 hour accuracy that we'll have the communication. So that's the flight dynamic system tools. I will go now on what we did with Scilab. So I just speak about the 1490 tool. I go on the Scilab ecosystem. So we are using Scilab version 5.4.1. We are using ScilabTEC. It's so Scilab toolbox developed and maintained by Cnes. It is not specific to Philae. You can download it through iTunes. There is around 400 functions that you can use to do attitude computation, maneuver computation, change of reference frame, and so on. So this toolbox is not specific to Philae. I should even say that it's quite specific to Earth because we don't have so many missions to small bodies. So we needed a toolbox really dedicated to our problem. So we developed Trace Lab. So it's developed and maintained by the team of some flight dynamic. And we are realizing data processing, different kind. I will tell you what kind of computation you're doing after, and also visualization. We also have some several graphical unit interface to make the life of operator a little more easy, because when you are doing operation, it's quite nice to have some graphical unit interface. So there is around 300 functions. It's not available to public because it's too much related to our mission. So probably a lot of functions are not interesting for the community. So the computation, we have a lot of, so we are able to read and write almost all input and output data of the flight dynamic system. We have a lot of data files, so it's a huge number of functions. We are able to handle all the mission frames transformation. We have several frames, frames related to the comet, to the landing site, to Rosetta, to Philae, to the scientific instruments. So we are able to change coordinates between all these frames. We are able to analyze the comet environment. So we receive the rotation model, gravity field outgassing, and we can produce some analysis to validate this model to see that there is no major problem. You have a typical example here. It's a model of outgassing. So you see the profile of the comet, and that's the acceleration created by the outgassing of the comet. So we are doing this kind of visualization and processing to check that the model is correct. We also have to do some analysis on the comet topography and digital terrain model. As Thierry said, we want to choose a place as smooth as possible, so we need to analyze the topography. So we're working either with global model, so analyzing basic properties like the volume, the center of mass. For local digital terrain model, we were doing some roughness analysis. We also have some mesh generation to try to have quite regular meshing at the surface of the body for specific analysis. We are doing a lot of statistical and probability analysis. And space mechanics, we like Monte Carlo shooting. You take, for example, your lander at the time of release, and you have uncertainties on the position, the velocity, the direction, on the gravity model. You do several trials, and you obtain several landing sites, and you look at the dispersion to try to simulate the reality. So this, we do it with the Fortune 90 tool, but after we have to analyze the result, and it was done with Scilab, with classical min, max, standard deviation, probability, function extraction, dispersion ellipse. We also have, for example, we have to derive the risk to land in the probability to land in a place free of boulder. When we see close view of the surface of the comet, there is rocks everywhere, and so we have to compute the probability to land, not to land in a boulder. So the scientific camera send us for several candidate landing sites. Files with boulder size and location, and we derive the probability to. And it was important to look at the risk between the different landing sites and find the best one. We're also doing geometry computation, like communication links between Rosetta and Philae. So for the visualization, we have two kind of, I would say two kind of plots. The low-level plot, where more or less you just take a file and make a visualization of the content of the file with really a minimum of processing. And we have high-level plots where you process several input files and you do some computation before to do a visualization. A typical example is this map. It's the so-called dynamic slope. Actually, it's the best map to do some ski on the surface of the comet. You compute the angle between the plumb line and the local normal to the surface, and it tells you really if what looks like a slope is a slope, if you will fall down. So it's very important for the landing, for the stability of the lander. So this kind of map, you just have latitude, longitude. The black line is the topography, is the curve of the comet, and the color is this angle of slope. So red, it's high slope, so we don't want to land on the red part. To do this kind of plot, you need the shape model, the rotation of the comet, the gravity model. So it's some processing before to obtain this result. So now, when do we use Scilab during the mission? Almost all the time. We use it for preparatory studies, so for comet environment analysis, mission design. You can see the kind of shape model we are using to prepare the mission. People believe that the comet was quite smooth, and so we are working on this kind of shape. They were derived from Hubble space image, actually. We also have to bring some support to the scientific community. Typical example is this picture. It was realized when Philae was still attached to Rosetta. So you have the solar array of Rosetta, and here you have the comet. And the camera on board, the camera Shiva on board Philae wanted to realize for communication purpose the pictures with the comet nucleus and the solar array. So we had to compute with Scilab, we did it actually, You have to tell them you can take the pictures for this date to have this configuration. We use it to develop the Philae dynamic system. We realize several prototypes directly with Scilab. We also use it to write the specification of need, to validate the tools when we have it. We very often use it to understand what's happened. Sometimes you have a result, you may believe it's a bug, but actually it's just a normal behavior, but you have to understand why. So it's very useful to have a Scilab to do this kind of analysis because you can go really deep in the detail. For the operation itself, we use it for the landing site selection process, so really a lot. For the landing and first science sequence. And so now the lander is hibernated. We hope that in the future we will have more light and he will wake up. So we are preparing this phase and we try still to determine where is the lander, so to the localization and the attitude. And we try also to predict the solar illumination. We are also, for scientists, reconstructing the event because they want to have accurate landing trajectory and the rebound and information on final landing site. So that will be the last slide of this section. Why to use Scilab? Operation is a very rigid process. When you are an operator, you have a procedure, so report, and you have to follow step by step what you have to do, and sometimes to take a decision, I go this or I go this, but everything is written. You have your tools. It's a very protected system. I told you that if you have a problem, you need at least to wait 24 hours to have maybe a patch, but it's even not sure. There is a high level of validation because you need to be sure of what you are doing. And you are committed to results, so you need to deliver the results on time and with the expected accuracy. So, for operation, improvisation is not welcome. The main problem is that Rosetta mission is a discovery mission. So, comets are almost terra incognita. It's the first time we orbit a comet. We have a lot of unforeseen requests and problems. Some teams ask you some support because there is something they didn't foresee and they need help. You can have some problem due to your tools that are not adapted to the environment. It's very expensive in terms of money and time to add new functionalities in the Philae dynamic system. So we need some flexibility for this mission. So we decided to use the Scilab ecosystem because with the toolbox you have some already made function with a quite level of validation, and after you can take different function and build your own program very easily, and you are quite sure of what you are doing. If you had to do equivalent code in Fortran, it will be much more longer. The second point was also that we decided that TraceLab will be the Sonk FD toolbox. So we don't have a contractor, we do what we want when we want. So if we need to build a program during operation, we can do it. So we really decided to use Scilab to have all this flexibility. So we're now on the conclusion. These pictures, front pictures, I find it funny. It's dust of the comets collected on a scientific instrument on board Rosetta. So it's cometary dust. Okay, so the first conclusion is thank you to Scilab and Scilab team. It was really a great tool to have for this mission. So we'll do a short conclusion on the scientific results. So first, it's still ongoing work. Rosetta is still around the comet collecting data. We expect to have the first publication of the Philae result obtained during the landing and the first science sequence for this summer. It will be in a science review. There is probably a decade of work for scientists to analyze the data and to produce models. So it's a huge amount of work. A few symbolic results. The main result is that comet Churyumov-Gerasimenko is much more complex than what was expected. You have seen the shape model we are using for the preparation, very smooth. It was a huge surprise to have so irregular shape with so many geological features. An important result was about the water. During the formation of solar system and Earth, the first stage, Earth doesn't have water, and water was in the outer part of the solar system, and we suppose that comet crashes on the Earth, brings water and elementary bricks for the chemistry of life. So people analyze the water from Rosetta, and it's different from the water from Earth. So it's a major result because it shows that at least this comet has water different from the one we found on Earth. It's not the case for all comets, but it was also a surprise because it was expected to have exactly the same water than what we have on Earth. Second result, that's a result shared between Rosetta and Philae. The comet is not magnetized. It's also a surprise because theorists making models of solar system are using magnetized comet, because if they don't do it, they are not able to reproduce the formation of the solar system. So it will be, I think, a huge work to take this result into account. Philae detects during the first jam a complex molecule with 3 carbons. And I told you that we also suspect that comets bring on Earth the elementary bricks for the chemistry of life. So if we are lucky, it could be an amino acid, so it will be a great news. But for the moment, we don't have the result of this molecule. So the future is the following: Rosetta continues its work. In August, it will be at the shortest distance from Sun. So there will be a maximum of outgassing. So it's very important to continue to observe the comet because it's an active surface. You see on this picture, there is this small jet appearing. So you have something dynamic. Philae, we hope for a wake-up. We are not completely confident, but actually the solar conditions are improving on the landing site. We are going to summer for the place. After August 2015, the solar geometry will degrade, so probably if the lander did not wake up before August, we will consider that he is lost. So we just finished by an advertising. There is currently an exhibition on the Champs-Élysées organized by Cnes, so at this subway station. And you can see a comet model 3 meter size and a full-scale mock-up of Philae. So if you are interested, you can go at this address to see the comet. Thank you.